What is the force per unit length on it when it is placed on a horizontal table and direction of the current is east to west? And second case, it is south to north. So the magnetic field is in this direction and the current is in this direction. So angle between them is 90. So what is going to be the force, guys? Force is equal to B into I into L into sine theta, which implies F by L is equal to BI sine theta. What is the value of B that is given? 3 into 10 power minus 5 into I is how much? 1 ampere. So sine theta is how much? Sine 90, that is going to be 1. So 3 into 10 power minus 5 Newton per meter is going to be the force per unit length. Okay, next. When the current is also flowing from south to north, what is going to be the force?
Zero, sir.
Anybody? 0. Very good. Since theta is 0 degrees. Hence, the conductor will not experience any force. Since we have understood this concept, we will try to understand the next concept, that is torque on current loop and magnetic dipole. Okay. See, do you guys remember this concept? If there is electric field and you place an electric dipole in external electric field, it starts experiencing torque. Do you guys remember this?
Yes, sir.
And what is the value of torque it experiences? It experiences
P
vector
into cross E vector sine theta.
That is right. It can also be written as P sine theta when you write it in terms of magnitude, where P stands for what? Electric dipole moment. E stands for electric field, and theta stands for the angle. Yeah, and theta stands for the angle between the dipole moment and the electric field. This is a known fact. Okay. Now what is going to happen is you have field here also. The only difference is electric field is replaced with magnetic field. Here also you have a dipole. Electric dipole is replaced with a magnetic dipole. So what do you think is going to happen when you place a magnetic dipole in external magnetic field? Again, it is going to experience torque. Clear? So for that, try to understand. There is a set of magnet, okay, north pole and the south pole, so that the magnetic field is from the north to the south pole. This is the direction of magnetic field. In that magnetic field, there is a coil that is placed, okay, and that coil is connected to a battery so that there is a current flowing in the loop. Guys, are you able to understand this point? So when the current is flowing in the loop, then we need to understand what exactly is going to happen to the coil. Okay. So the dimensions of the coil are like this. From B to C, the distance is A. From C to D, the distance is B. Okay. So having these 2 points in mind, I would like to show and explain how it works. So I hope you guys are able to see me, right? So these are the 2 magnets and the magnetic field is in this way. In that magnetic field, there is a coil that is placed. And the coil is carrying a current. Okay. So the coil that is given there is in the shape of a rectangle. Correct? So it's in the shape of a rectangle. So rectangle can be made of 4 linear conductors. Right, guys? Are you able to understand? Suppose I take this point as A and this point as B, and this point as C and this point as B. AB is in this direction and magnetic field is in this direction. So listen, AB is in this direction and BC is in this direction, correct? So, AB is in this direction, magnetic field is in this direction. So, what is the angle between the current in AB and B? And that is the magnetic field. Obviously, it is how much? How much is
90,
the value?
sir.
It is 90, correct. Magnetic field is magnetic field this direction, current in this direction. So if you see, it is 90 only. You're right. Okay. When current is in this direction, when you do I into L cross B, okay, from L you need to curl your fingers towards B, then you can see that this conductor experiences a force in the downward direction. So the wire AB experiences a force in the direction. Accepted? Am I clear till this point? Okay. Am I clear, guys? Similarly,
Sir.
BC is in this direction. Okay. BC, current in BC is in this direction. Magnetic field is also in the same direction. So, what will be the value of force experienced by BC?
0, sir.
0. Similarly, C to D is in this direction. It is towards me. Current is towards me. And the magnetic field is still in this direction. Okay. The current is like this. And the magnetic field is like this. Now, what is going to happen between both?
Sir, force experience upward, sir.
Perfect. The force will be experienced in the upward direction. Right? Because current in this direction, magnetic field in this direction. So force will be in upward. So remember, on AB, it is downward. BC, there is no force. CD, it is upward. What about DC? DC is in this direction. Magnetic field is in this direction. So angle between them is how much?
0, sir.
180. Magnetic field this direction, current in this direction. So angle between them is 180. Sine 180 is also 0. Now comes an important question. This branch is experiencing force in downward direction. This branch is experiencing force in upward direction. And these two branches are experiencing no force at all. Right? Had BC and CD not existed, okay, had BC and CD not existed, what would have happened to AB? It would have started moving in the downward direction. And what would have happened to CD? It would have started moving in the upward direction. Means AB will be moving like this and CD will be moving like this. You're able to understand this? So initially they're like this, they'll start moving like this. But this BC and AD are there, no? They are holding these two in such a way that this will try to move in this direction, this will try to move in the upward direction, so that they will start. What is happening? They start rotating. You're able to understand this, guys? Am I clear?
Yes, sir.
Yes, sir.
What will happen is, when you have a current carrying coil that is placed in the magnetic field, it starts experiencing torque. And what is the value of torque? That is what you're going to calculate now. Apart from this, is there any other doubt? Is it clear? Shall I proceed? So, understand. Okay. Now, I will try to make it slightly simple, okay? So that you guys can understand it better. Let's say this is the north pole of the magnet. This is the south pole of the magnet. Okay, let me call this as 1, 2, 3, and 4. Okay.
Sir, I can't see your screen, sir.
That's so. Now,
Yes, sir.
Yes, sir.
okay. So I just changed the diagram for simplicity. Okay. So magnetic field is going to be from north to south pole. Current is flowing in the clockwise direction. So, what is the force experienced by the first conductor? What is the force experienced by the first conductor?
Downwards, sir.
I'm not asking about direction, I'm asking about value. I into L into B. And remember, this side is of value B and this side is of value A. Formula F is equal to BIS sin theta. What is there? What makes you people think so much? I into what is the length of side 1? B into the magnetic field is capital B. Sine of how much?
90.
That's it.
90.
Yes, Bi into B is the value of the force experienced by the first conductor. Now, let's put the vector symbol on top of it. Now, tell me the direction.
It will be downwards, sir.
That's right. It is minus K. Okay, force experienced by the second conductor is 0. Same is the case for the force experienced by fourth. Then what is F3 vector, guys? I into B into capital B into sine 90 degrees. That will be B into I into B in the direction of K cap. Accepted?
Yes, sir.
Now, what is the net force? So net force is 0. Net force is 0. Then what can you say about the net torque? So torque experienced by the first conductor is how much? What is the torque experienced by the first conductor? That is force into, okay, I'll make it like this. So what is the vector formula for torque, guys? R vector cross F vector. So what is the value of R? So this whole coil is going to revolve about its center of mass, about an axis passing through center of mass. So how much is this distance? This distance is A by 2. Okay. So can I write it as A by 2 in the direction of I cap cross F vector is how much, guys? Bi into B in the direction of minus K. Is there anyone having doubt in this step? So A by 2 times I cap cross B into I into B into minus K. So torque is equal to bi a into b the whole divided by 2 into I cap cross minus k cap. Tell me what is I cross k? What is I cross k? It is minus j. Minus of minus j will be plus j. I j k. I cross k is minus j. Na? So minus of minus will give you plus j. So torque experienced by the first wire is this much. Similarly, torque experienced by second is 0. Torque experienced by third is how much? R3 vector cross F3 vector. Okay. So 3 is here. What is the distance from the third coil to the center? This distance is A by 2. So this will be A by 2 times. What is this direction, guys? So what is this direction?
Sir,
Okay, what is
it
this direction?
cap?
Sorry?
K cap?
This minus I cap. Negative x-axis, no.
Okay.
Yeah. Minus I cap cross. What is the value of F3? B into I into B in the direction of K cap. So this will also be B into I into A into B divided by 2 in the direction of plus J cap. This will also be 2. Similarly, torque experienced by, so net torque is going to be torque 1 vector plus torque 2 vector. This will be B into I into AB divided by 2 times J cap plus B into I into AB divided by 2 times J cap. This is BI by 2 into what is the value of AB? It is A in terms of J cap. Okay, I will write it AB only. Okay. Here, note
Sir, one doubt, sir.
area of rectangle. Tell me.
Sir, is it
Sorry.
torque
The
1 plus torque 2 or torque 3?
torque 3. Thank you. It is torque 3 and the denominator, the 2 is also gone. So area of rectangle, if I call it as A, that's right. What you asked is right. Torque 1 plus torque 3 is this value. So if I take the area of the rectangle as A, it is nothing but A into B. So I will get BIA in the direction of A cap as the net torque. Okay. This is where certain important points come into picture. So there is a concept called as magnetic dipole moment. So the product of current and area is what we call it as magnetic dipole moment. So if that is the case, then torque can be written as M into B in the direction of J cap. Okay. So from this I can conclude the torque as a vector can also be written as M vector cross B vector. Okay. So is this not something similar to P vector cross E vector? Instead of P, you have M. Instead of E, you have B. That's it. Okay. Here, I directly wrote it as M vector cross B vector because I didn't take the coil to be at some tilted angle. I took it exactly perpendicular. That is why I got sine 90. That's why it's 1, no? But the generic formula for torque experienced by a magnetic dipole and magnetic field is torque is equal to m vector cross b vector. Okay, am I clear with this?
Yes, sir.
So m is written as Ia, right? Sometimes magnetic dipole moment is also written as n into I into A, where n stands for number of turns. Here in this case, there is only one turn, so I wrote it as I into A. The number of turns are capital N, we write it as capital N into I into A. Okay. So let me show you what is the formula. Okay. So keeping all these points in mind, let's try out the problem. So there is a 100-turn closely wound circular coil of radius 10 centimeter that carries a current of 3.2 ampere. So write down capital N is how much? 100. Radius is 10 into 10 power minus 2 meter. Current is 3.2 ampere. What is the field at the center of the coil? P is equal to mu naught Ni divided by 2 into R. Right, with this you can calculate the magnetic field at the center. What is the magnetic moment of the coil? So what is the formula for magnetic moment? Just now I told you. N into I into A. So 100 into I is 3.2 into area is pi r square, where R is 10 into 10 power minus 2 the whole square. Okay. So this is the magnetic moment. Next. The coil is placed in a vertical plane and is free to rotate about a horizontal axis, which coincides with its diameter. So there is a uniform magnetic field of 2 Tesla in the horizontal direction exists such that the initially axis of the coil is in the direction of the field. The coil rotates through an angle of 90 degrees under the influence of magnetic field. Okay. What are the magnitudes of the torque on the coil in the initial and final position? Guys, are you able to visualize what they're saying? Did you understand what they're saying?
Yes.
So here the question is, there is a horizontal magnetic field existing and the coil is placed in such a way that the axis of the coil is in the direction of magnetic field. So generally from the first chapter we know that the aerial vector will be in this direction, right? So what is going to be the torque? So the angle between area and B is 0. So torque will be 0. So what about the final torque? At the final torque, theta will be equal to 90 degrees because it had made a rotation. Let me explain. I'll show you a video and explain this. See, if this is the coil, okay. If this is the coil, then if the current is flowing in the anti-clockwise direction when you see from this side, you take your right hand, okay, and curl the fingers of your right hand in the direction of current. I repeat, the coil is there, current is in anti-clockwise direction. Take the right hand and curl the fingers of your right hand in the direction of current and extend your thumb. The thumb will give you the direction of the magnetic dipole moment. Okay. So in this case, what has happened is there is a horizontal magnetic field, and the coil is initially placed in such a way that the axis of this coil, what is the axis of this coil? This is the axis of this coil. So axis of the coil is in the direction of magnetic field. Okay. So current should be in the anti-clockwise or clockwise direction. Then when you apply this right hand thumb rule, then you will get the answer as 0. So theta is equal to 0. That is why it is getting cancelled out. Now what has happened is the magnetic field is like this. The coil has rotated in such a way that the axis is making 90 degrees with the magnetic field. So it is in this direction, magnetic field is in this direction. So it is making 90 degrees with the axis of the axis. Hence, guys, are you able to see my screen?
Yes, sir.
Hence, theta will be equal to 90 degrees in the second case. So in the final case, torque will be equal to m into b into sine theta. M you would have calculated from here. So m you would have calculated from here. M into b is 2 into sine theta. That is sine 90 is going to give you the answer. That is 20 Newton meter. Okay.
Sir, I can't see the screen, sir.
Others?
It's visible, sir.
You can see,
It's
sir.
visible, sir.
Now
This
it's visible.
angular speed, yeah, this angular speed and moment of inertia, I will explain it in the next chapter. Okay. I don't want to explain now and confuse you. Rather, we can go to the next problem. So there is a current carrying circular loop which lies on a smooth horizontal plane. Can uniform magnetic field be set up in such a manner that the loop turns around itself? That is, it turns about the vertical axis. Okay, that is the first question. Second is, a current carrying circular loop is located in uniform external magnetic field. If the loop is free to turn, what is the orientation of stable equilibrium? Show that in this orientation, the flux of the total field, that is external field plus field produced by the loop, is maximum. And in the third case, a loop of irregular shape carrying a current is located in external magnetic field. If the wire is flexible, why does it change to a circular loop? Okay. So first, let's come back. So there is a current carrying circular loop lying on a smooth horizontal plane. Can you generate magnetic field in such a way that the loop turns about itself? So they want the loop to turn in this way. Is it possible? So let me show how they're explaining. See, the coil is lying like this. This is the vertical axis. They want. So the coil is lying like this. Okay. They want the coil to turn in this way. Is it possible? You guys think and tell me. They want the coil to turn like this. That is the meaning of turning about itself. So is it possible? What do you think is the answer? Is it possible? So if this coil has to turn in this direction, then torque should act here and torque should act here. Right, let me read the question again. So current carrying circular loop lies on a smooth horizontal plane. Can a uniform magnetic field be set up? Turns about the vertical axis. Okay. Now we know the formula for torque. So what is the formula for torque? M vector cross B vector, right? Guys, you need to concentrate a lot for understanding this. So torque is equal to M vector cross B vector. So what will be the direction of torque with respect to M and B? What will be the direction of torque with respect to M and B? You're doing cross product, guys. So what will be the direction of torque? Why is no one answering? Is my question clear or not? So if I say C vector is equal to A vector plus B vector, how is C vector with respect to A and B?
That is the resultant vector. C vector is the
C vector's direction with respect to A and B is what I'm asking. So if you're not able to answer in terms of cross product, you're not going to understand this question. There is no point showing also.
clockwise.
Sorry?
Clockwise.
Nothing to do with clock. See, I last class itself I told you guys, please revise cross product and come before next class. You guys are not understanding cross product. This chapter is of no use. I cannot teach. I think this is the nth time I'm saying whenever you do cross product between two vectors, the resultant will be perpendicular to both the vectors for which you're doing cross product. Okay, leave. So you're not going to understand this question. Leave. Let's go to the next concept. So this concept is the beginning of next chapter. Which one? This one. So the beginning of next chapter, but I will explain it there. So last topic that is there in this chapter is moving coil galvanometer. So write down the heading as moving coil galvanometer. So moving coil galvanometer in short form is also called as MCG. Okay. So what exactly is this moving coil galvanometer? Let's see. I'll show you a diagram. Just give me a second, guys. Listen. See, this is how a moving coil galvanometer looks like. Okay. So if you ask me why do we use a moving coil galvanometer, what do you think is the answer? So a moving coil galvanometer is basically used to detect the presence of current. Okay. So then what is the difference between a galvanometer and an ammeter? I think I've already told this in the case of Wheatstone bridge. What is the difference between a moving coil galvanometer or a galvanometer for that matter and an ammeter? Let's at least try, no? Am I audible or not?
Sir,
Yes.
it determines the rate of, it gives the, which is, it detects the measuring electric current.
Very okay. You mean to say it will detect whether current is flowing or not. So galvanometer will detect current flowing through it, whereas ammeter is a device which is used to measure the current flowing through it. So measure means it will tell you what is the exact value of the current that is flowing through that particular device. Okay. So
Sir,
having all these points in mind, tell me now. Tell me what is the
sir,
doubt?
galvanometer shows the both direction as well as magnitude. No, sir.
No, no. Galvanometer will not show the direction of current. If the galvanometer starts getting deflected to the right, it doesn't mean current is in clockwise direction. No.
Oh, okay.
Okay. So it doesn't show the direction of current, rather it will only show the presence of current. That is it. So if you see a galvanometer's calibration will be done at the center. Okay. So when it is done at the center, it can turn in either of the directions. So one thing we need to understand is, if you see when the current is flowing through it, there is a pointer, right? This pointer is experiencing a rotational force, nothing but a torque, right? So a pointer is able to show the division that is there on the scale by experiencing a torque when current is flowing through it. So having all these points in mind, let's think on what principle does a galvanometer work. Okay, so first we need to understand the principle on which a galvanometer works. So galvanometer basically, please write it down. Please write down the heading as principle of a moving coil galvanometer. Principle of a moving coil galvanometer. Okay. Write it down. It works on the principle that a current carrying coil, it works on the principle that a current carrying coil placed in external magnetic field, experiences torque.
Could you repeat it again, sir?
I'm saying when a current carrying coil is placed in external magnetic field, it experiences torque. So that is the principle on which it works. So if it has to experience torque, obviously what are all the things that we need? We need an external magnetic field in the first place, right? So for generating external magnetic field only, you have two magnets which are in the shape of concave.
Recording in progress.
1 minute. Students, just a minute. I will show you. Students, are you able to see me?
No, sir.
No, sir.
No, sir.
Okay. I think there is some issue, but okay. Are you able to see the screen now?
Yes, sir.
Yes, sir.
Do your video and explain, that's better.
Galvanometer. A galvanometer is a device used to detect current.
So it is a device which is used to detect current with appropriate modification. Means you can make this galvanometer into a measuring device as well by doing certain changes. What those changes are, we will see later. Okay.
Sir, your screen is stuck.
No, I only paused it.
No, sir. It's
No,
not
sir.
showing the video screen. It's showing the file you have kept the video, sir.
Yes, sir.
This one. Now you are able to see.
No, sir. It's still
No,
frozen.
sir.
Still frozen. Okay. Now.
Yes, sir. We are able to see.
Yes, sir.
Galvanometer is a device used to detect current. With appropriate modification, it can be converted into an ammeter, which can measure currents of the order of an ampere, or milliammeter to measure currents.
So what will happen is, by using, see, generally galvanometer is a sensitive device. It will only detect the presence of current. But by doing certain modifications, we'll be learning that also. Conversion of a galvanometer into ammeter, conversion of galvanometer into voltmeter, all those things we'll be learning. Okay. So you can make those changes and convert it into a measuring device as
The
well.
range of milliamperes, or the currents. Coil on thin copper light rectangle.
So if you look at the construction, guys, let's think of this. A galvanometer works on what principle? It works on the principle that a current carrying coil is placed in external magnetic field, it starts experiencing torque, right? So for that you need a current carrying coil, and to hold that current carrying coil, you have a rectangular frame like this. So you're able to see from the top. So light rectangular frame on which a coil of thin copper wire is wound is pivoted between two almost frictionless pivots. Pivots means the things which are holding. Now see how it is happening, okay?
Rectangular frame on which a coil on thin copper wire is wound is pivoted between two almost frictionless pivots and placed between cylindrical poles.
Okay. Now, obviously, to generate the external magnetic field, you need two magnets. So those magnets are cut in the shape of a concave so that they will generate a field called as radial field. Okay, what that radial field is, we will see it now. Guys, are able to understand? And the pointer is connected to this coil. So galvanometer center will be 0 will be at the center, and either side you will have divisions.
Of a permanent magnet so that it can freely rotate in the region between the poles. The poles are suitably shaped, and a small soft iron cylindrical core is placed at the axis of the coil, free from the coil to obtain uniform magnetic field. When the current is passed through the coil,
You're able to see that green color line which passed. So when the current starts flowing through this coil will start rotating. When the coil starts rotating, what is connected to the coil? This pointer, no? This pointer will also start rotating.
a torque acts on it and is deflected. This deflection causes the restoring torque in the spiral springs attached at the two ends of the coil, and the coil attains a steady deflection. The pointer attached to the coil moves on a scale and indicates the current. Principle and working. The torque developed in the coil due to the current passing through it is given by tau equals to.
This and all I'll explain. Is it clear till this step? Did you guys understand how it works? Okay, remaining part I will explain. See. So if you look at your textbook, so you have a scale whose 0 is here, okay, and you have divisions on either of the sides, and this is the coil, and this SP stands for hairspring. So they call it as hairspring because it restores the position of the pointer. That is, as soon as you stop the current, what will happen is the pointer will not know that it is supposed to come back to 0. So you need a spring in which the energy is stored and it comes back to its original position. Okay. So keeping all these facts in mind, can I say that the torque experienced by the coil is equal to Ni A into B sine theta? And remember, theta is equal to 90 degrees due to the radial field. So please make a note of this. What is the radial field? It is a uniform field which is getting generated towards the center of the coil. Okay. Due to the radial field, theta is equal to 90. If you substitute it here, torque will be equal to Ni A into B. Okay, let me call this as equation number 1. So this is the torque experienced due to the current. But the spring will experience a restoring torque whose value is given as K phi. Okay, so what should happen is this external torque NIAB should be equal to K phi. Then NIAB, if I write it as equal to K phi, then I'll get phi is equal to NIAB divided by K, where that K is called as the torsional constant. K is called as the torsional constant. Okay, this value has to be remembered. So this is the amount of deflection the coil will start experiencing when current is passed through it. Okay, I will write it neatly again. Listen. So these are the steps, guys. So torque is equal to NIAB sine theta, and put theta is equal to 90 degrees in this, then torque will be equal to NIA into B. Okay. So let this be 1. But NIAB is also equal to K into phi, which is the restoring torque. And phi will be equal to NIAB the whole divided by K. And this is the value to be remembered. Okay. So these are the basics with respect to a galvanometer. Okay. Now, if I rearrange this equation, phi divided by I, this can be written as N into A into B divided by kappa. Okay. This phi divided by I Okay, this phi divided by I is what is called as current sensitivity. Means the amount of deflection, so you're able to see, right? You have 0, let's say 2 units of deflection. So if the pointer is showing 2 units of deflection on passage of 1 ampere of current, then phi divided by I is what is called as current sensitivity. So you can define it like this: amount of deflection per unit current. So amount of deflection per unit current is what we call it as current sensitivity. Similarly, if you are able to define phi divided by V, then this is called as voltage sensitivity. Okay. And the last thing that you are supposed to know is the reciprocal of current sensitivity, that is I by phi. This is what is called as figure of merit. This is called as figure of merit, which can also be told as, which is also measured in ampere per division. Okay, these are the important keywords that you're supposed to know with respect to a galvanometer. Okay, guys, any doubt till this point? Anything you want me to explain again?
Sir, can you repeat I by psi equals figure of, what is it?
Figure of merit, MERIT.
Okay.
Okay, it's called figure of merit. Okay, since you asked, I'll explain it. Okay, what is the significance of this? See, this is 0 now. You're able to see small lines. You have every measuring device will have a least count, right? So here from 0, if I have to move it to the immediate division, means for the deflection to be 1, how much current is needed is what is called as figure of merit. Means what I'm trying to say is, to exactly produce a deflection of 1 unit, how much current am I supposed to pass through the galvanometer is what we call it as figure of merit. And you have this experiment in your practicals. You will be doing an experiment based on this. Okay. So these are the basic steps with respect to a moving coil galvanometer. Okay. So I'm giving you some time to absorb this concept. Before next class, I want you to revise these concepts so that you will understand the next 2 concepts that I'm going to explain. And I repeat it again, if you guys have not gone through the cross product of vectors, I have recorded a video and put on YouTube. Go through it. It is just 13 minutes. In 13 minutes, I've covered everything. Just go through it and come before next class, or else I can't help you. Your cross product of vectors concept is very bad. I'm talking about everyone.
Okay, sir.
Yes, sir.
Yes. So any other doubt from today's class? By next class, this chapter will be over.
Okay.
Yeah. Okay, then no doubt means we can log off.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.